Do you hear me?
Yep.
All right, and recording has started?
Yeah. Yeah.
All right, so let's get started. So signature constraints is actually not a very complicated thing. I'm just going to contradict Richard right there. But what is really complicated is the stuff that it enables and the reason why people really want it, which is rolling upgrades. And you can't really divorce the two because there would be no point in signature constraints if we did not want a better upgrade story. So I'm going to cover the slightly wider topic today as well. Okay, so we're going to talk about what are rolling upgrades and how will they work in Corda. Then we're going to discuss signature constraints. Then we're going to cover what's working in 4.0 and what's targeted for future releases. And then we're going to talk about package namespace ownership and what that is and why it's there as well. All right? Okay. So rolling upgrades, I'm sure most of you know this already, but just for people who have never worked on distributed systems before, rolling upgrade is where you have many servers doing things or many computers doing things, and you want to upgrade them all to version 2 from version 1, but you can't do it simultaneously, either because they're not all controlled by you or because they are, but you don't want to take the service offline. And this typically crops up on the web, where browsers can't handle node outages of any kind. Basically, if a web server is offline, then the user gets an error. So to do any kind of upgrade, you need multiple web servers, and you need to spray traffic across them and then roll them from version 1 to version 2. And during this time, this is a really complicated thing, because during this time, new and old versions of the software coexist, and it's very easy for this to go wrong. When working on new features, developers have to remember that old software may have to interact with software that's effectively from the future, right? It's creating data that wasn't known about at the time version 1 was made. It's changing protocols and things potentially in ways that were not anticipated, and yet the old software must be able to work and continue working. Moreover, what makes it even more complicated is if you have a partial rollout that then rolls back. So you go from version 2 back to running version 1 because you find a flaw, for example. So this process of doing rolling upgrades back and forth is very complicated, and unfortunately, and if you look at the history of outages in the IT sector, then making computer systems that are reliable when you're not touching them is actually quite straightforward. It's a well-known thing. Almost all outages are caused by attempts to change the system. So in Corda, we have a fractal problem, actually, because not only must Corda nodes be able to roll out in a rolling upgrade setup, but also applications that run on top of it. And therefore, it's not enough for us to solve this problem for ourselves. We've got to solve it for our developers as well. The alternative is that you don't do a rolling upgrade. Instead, you suspend the system. For example, over a weekend, everyone upgrades together, or all the machines are upgraded, all the servers are upgraded, and then you test it, and then you carry on Monday. That simplifies things a lot because the system is not live while the upgrade takes place. And sometimes, especially in some industries, that's expected and you can get away from it. You can get away with it, rather, but in many industries, it's no longer considered acceptable. You want 24/7 operation. So here's the current state of play. Today, we launched Corda 4.0 and rolling upgrades for both Corda and apps, mostly but not entirely supported in Corda 4.0. There are a few little bits and pieces that will follow in 4.x releases. You know, we just had to get 4.0 out the door, so there are a few details that can be fixed in follow-up releases. We had to do all the ones that affect the core data model and protocols in 4.0, but we couldn't. A few things could be left. And the goal is that it'll take a bit of time to get this right because it is a complex thing, but by the end of the 4.x cycle, they should be working well, and you should be able to do them quite straightforwardly for both Corda and apps. Now, that said, without a doubt, there will be disasters and outages because this is just such a common cause of problems in the software business. In particular, apps must be designed for rolling upgrade in a decentralized system, which is something that many of our users will not have ever had to write before, either because they've never worked on very large-scale websites, or they've never worked on distributed software at all. And then the fact that this is not even distributed software, this is decentralized software, so there could be attackers in it, complicates things still further. And of course, not only app developers must think about this, but node operators must also learn how to do it safely, and we'll talk about what that means later. So yeah, if you can design things such as you have maintenance hours, then That's a recommendation we should be willing to make, for not every kind of application needs 24/7 operation, and it does have a cost and risk. Okay, so what's needed to make this work? Well, the eponymous signature constraints that we hear so much about, but that's not by itself enough. It's really helpful if you can turn your node off, upgrade it, and then turn it back on again, which means that you really want networking stacks and protocols that can tolerate like nodes going away and coming back. You don't have to do things that way. Like I said, the web doesn't have that support, which is why you end up with load balancers and DNS balancing, and it's incredibly convoluted to make the web highly available because web browsers don't retry in case of errors. They can't handle the server that's temporarily gone. Web apps don't work offline. But in Corda, we did design things so that if a node goes away, then other nodes will just pause and wait for it to come back, and you can restart your node to do things to it without creating errors at the other side. Again, that requires app developers to cooperate, and not all of them do because we don't always help explain how to do that, and we don't always provide everything they need yet, but that will come. You need two-phase rollouts of new features. We'll get to that a bit later. And then finally, you do need good communication with all the parties who are upgrading. You probably need some way to monitor what they're doing. So if they're not if they're not doing what they're supposed to at any particular point in the upgrade process, you find out and you can talk to them and help them get it right. And all this stuff currently is punted to the users, but in future versions of the platform, I'm sure this is a common need that will come up again and again, some sort of like monitoring of what's going on in your business network and the users of your apps so you can coordinate them. And today, when I say coordinate, what I mean is like emailing them is fine. Okay, so signature constraints. What is a distributed ledger? This is going to sound a little bit basic or condescending given what we do, but I'm going to go over it anyway just so we're super clear. Right, a blockchain is a kind of a database. It's a ledger made up of both data and code simultaneously. So it's not just data, like in beginners sort of my first database. It's more like the combination of database tables and stored procedures. In the first generation, we had Bitcoin, where the code was this like tiny little inline assembly language that in theory was quite powerful, and then shortly after release, Satoshi realized he had like screwed it up and made a lot of mistakes. So he basically switched off most of that scripting language, as he called it. And unfortunately, it never really recovered. So it's not useful for very much, but it established the concept that on a blockchain system, you have code and data living in the same database. And then the data was, of course, the value fields in transactions. You could only store values, which resulted in lots of weird hacks, like people encoding data into the prices in a transaction and stuff. So second generation was Ethereum, in which they decided the code is a sort of stateful object in the object-oriented programming sense, and the data is like every object. What they call a smart contract is a stateful object, has like a key value store associated with it. So code and data are tightly bound together in the way that you would expect in object-oriented programming. Well, close to what you would expect. And then, I don't know if the Ethereum guys would agree with this, but hey, I wrote these slides, so I can call Corda third-gen system. Which is where we go back to the Bitcoin's data model but upgraded. So the code is sort of little bytecode language again, like in Bitcoin, but it's Java bytecode. And we don't inline it into the transaction. We don't not every transaction contains a complete copy of every bit of code. We have this notion of attachments where the transaction refers to a bit of code by hash, and then that means you can have much bigger programs and they're not copied around constantly over and over again. And then for data, it's fixed. Like in Bitcoin, once put on the ledger, it stays, it's immutable. And we allow arbitrary serialized object graphs, or near arbitrary. So the key thing is that we have this separation of code and data. So what are constraints? Well, both Bitcoin and Ethereum have a very, very hard link between the code and the data. Basically, when you put things on the ledger, you upload your code and you upload your data. And then after that, the code can't be changed, and the data can't really be divorced from the code. So that means, by implication, there's no such thing as upgrading code in Bitcoin or Ethereum by design, which is partly because upgrades are mind-blowingly difficult in any kind of distributed system, and they're afraid of it. I know they're afraid of it because I used to work in that Bitcoin community, and we were all terrified of upgrades because we knew how easy it was to break things. And it's partly a philosophical thing. They turned this weakness into a strength by talking about code as law, or a perceived strength as they saw it. So they said, well, this is how you've got total certainty that people can't screw you. The code can't be upgraded. So if you read it, then it will stay with what you read. Now on Corda, we don't expect people to write perfect code. We don't really invest in things like really crazy advanced programming languages or anything like that. We sort of expect that people will make mistakes, and we expect that business requirements will change, and therefore that both data and code will need to change, so we invest heavily in upgrades instead. And in Corda, data states is linked to code in a vague way, not a hard way. Or I should say it can be linked in a vague way. So when you create data on the ledger, you can specify that the code that is going to be used with that data can change according to certain rules. Now, the simplest rule is actually that it may not change. This is called a hash constraint, and that's Bitcoin and Ethereum style. Once created, it can never be changed. That exists partly to make us seem more blockchainy a little bit, partly because it was easy to implement, and partly because we can imagine in a big future network where some applications are just so critical to the economy, like a cash app, for example, that the whole notion of upgrading it is just nonsense, and you could never get enough agreement, and people would always worry. So we just don't allow upgrades in that case, or we say the user can select that they don't want to allow upgrades. Then we have this code that's whitelisted by the zone operator, and that was added in Corda 3 as a quick